Today, we're starting a unit on systems of linear equations. This lesson will provide a brief introduction to systems and then move into Lesson 1, Solving Systems by Graphing. Let's start with some basic vocabulary. Now, normally, if this lesson were live, I would take a moment to ask my students what they think a system is. I don't expect them to immediately provide me with a mathematical definition. In fact, many are able to provide examples of the types of systems they already have known of. Recently, one student mentioned the central nervous system in the body. Another student brought up various gaming systems like PC, Xbox, PlayStation. All of these systems have something in common. They're made up of smaller parts that work together as a whole. The same is true for systems of equations. A system of linear equations is a set of two or more equations that have the same variables. So they have the same unknowns, it's just two different relationships working together as one whole. And then another thing that we take a look at vocabulary-wise, since we're going to be solving systems, we need to define what a solution is to a system. A solution of a system of equations is an ordered pair, so it's going to look like a point, x, y, that satisfies all equations in the system. So one nice thing about this chapter is you're going to know if you have a 100% on any quiz or test before you even turn it in to need to be graded, because there is a way to check your solution. So let's just take a moment and look back at what we've done in the past. In the past, when we've solved equations, we've just had a single variable and a single equation. You can see the example that I have up here, right? We distribute, we combine like terms, we use inverse operations, all to get to, in this example, x is equal to 7. Do you remember how we checked our answers in the past? I'm going to ink right here on the slide. So to check your answer, we got x is equal to 7. So if I want to confirm that x is in fact equal to 7, I'm going to take that value and I'm going to substitute it in for x and then simplify, see what we get. So I'm going to bring everything else down, so I should have 2 times the quantity of 3 times 7 minus 1. And we want to see if it really does equal 40. I like to put a little question mark right here. So first thing I have to do, order of operations, I would have to multiply. 3 times 7 is 21. So I have 2 times the quantity of 21 minus 1 equals 40. 21 minus 1 would be 20. There we are. And 2 times 20 is in fact 40. So you can check whether you had a solution to an equation in the past, if you were correct or not, by just substituting that value back into your equation. The process is going to be very, very similar for systems. So to check a solution for a system, we must substitute the values of x and y into each equation in the system. Again, system means you have multiple parts working together as a whole, so you have to test all of the equations in the system to see if you have the correct solution. So if the point is a solution to each equation in the system, then it's a solution to that system. Okay, so first example we're going to go through is just testing whether or not you have a point that is a solution to the system. This is going to set you up for success for checking your answers to your own problems that you're going to solve within the unit. So example 1 says, determine whether point 4, -1 is a solution to the system. So here we have our first system of equations. It's made of 2, 3x plus y equals 11, and x minus 2y is equal to 6. One thing that I do want to mention here, whenever we're working with systems, organization is really important. So you're going to see me number my equations a lot, just so it's easy to see what's going on and which equation I'm working with. So I'm going to do one at a time. Since we have an ordered pair here, remember your x-coordinate is always first, your y-coordinate is always second. It's always alphabetical if you forget. And we're just going to take those values for x and y and substitute them into the equation one at a time. So for the first equation, this would look like 3 times my x value, which is 4, plus y, which happens to be -1 here. And we want to see if we're going to get 11. So this is the same process that I just showed you with that example from the past. So order of operations here, I do 3 times 4. That will give me 12 plus -1. and that is in fact equal to 11. So far, so good. That point is a solution to the first equation in the system. We're going to check the second one. So the process begins again. We have x is equal to 4, y is equal to -1. We're just going to substitute those values into here. So 4 minus 2 times -1 is equal to 6. Let's see if that's actually going to work out. So I see multiplication first, -2 times -1, that gives me +2. So this would be 4 plus 2. And yes, that looks like it's going to work out just fine. Since those values for x and y worked in both equations in the system, then I can say yes, point 4, -1 is a solution to the system. Very good. Okay, it's your turn. Let's give it a try. So same system actually, 3x plus y equals 11, and x minus 2y is equal to 6. This time I'd like you to test the point 2, 5. Go ahead and pause the video and give it a try. Alright, so if you pause the video and you want to check your work to see if you are accurate, I'm going to do the same thing. I'm going to substitute those values and just show you what my work would look like. So this would be 3 times my x value, which is 2, plus 5, see if we get 11 there. 3 times 2 is 6. 6 plus 5 is 11, so far so good, works in the first equation. Okay, so let me try in the second equation. This is x minus 2y, so 2 minus 2 times 5 is equal to 6. I can already see what's going to happen here. So if I have -2 times 5, that'll be -10. So I'm looking at 2 minus 10. Certainly not going to be equal to -6. That's -8. Not true. So remember, a system, it has to, if you have a solution to a system, it has to work for both. So here it did not, so I would say no. 0.25 is not a solution to the system. Okay, now that we have an idea of how to check our answers, once we have one, let's take a look at how we're going to solve a system. There are many ways to solve a system of linear equations. What we're going to be focusing on today is solving by graphing, because I think graphing is something that we've done pretty recently, so it'll be easy to make that transition here. So one thing I want you to remember from the past is the answer to this question. So what does a graph of an equation actually represent? Well, a graph represents all solutions to an equation. Remember, if you have a 2-variable equation like y is equal to 2x plus 1, there are infinitely many solutions. It's impossible to write them all, which is why we create graphs. So graph is like a picture of all of the answers to an equation. So when we're going to solve a system by graphing, first thing we're going to have to do is create that image of all of the answers to each equation in the system. So you're going to graph the system, but on the same coordinate plane. For us, since our systems only have 2 equations, we're going to see 2 lines graphed on the coordinate plane. The solution to a system can be found at the intersection of all lines on the graph. So let's take a look at an example here. So this is example 3a. Notice that these 2 equations have already been graphed for you. So you can see what we have here. Can you spot the answer? Yeah, those 2 lines intersect at the ordered pair 3, -3. So your answer is 3, -3. That's the solution to the system. And we know how to check our answer, so I just want to demonstrate that here. Remember, my x value is 3, my y value is -3. Let's just double check to see if that's correct. So substituting into here, the first equation, I'm going to have -3 is equal to 3 times my x value, also 3. There are a lot of 3's in here. Minus 12. So I want to see if it's going to be equal on both sides. So I have -3 is equal to 3 times 3 is 9. Minus 12, that will give me -3. So far, so good. Okay, let's test the other one. I'm getting these equations from the labels that I'm seeing here in the graph. So I have -3 equals -2 times +3 plus 3. So this time, multiplying -2 and 3, that will give me -6. Everything else comes down. And -6 plus 3 is, in fact, -3. So you can see the solution on the graph. You can see that the solution works in both of the equations in the work that I've just done. That's all there is to it. So let's try another one. So here's another graph of a system. What's the solution? If you said that those two lines intersected at point -3, +1, you are exactly correct. And again, I want to show you how that works in both of the equations that are listed there. So let's go through and substitute our values into each equation, see that we get a true result. So my x is -3, my y is 1. So in the first equation, this will be 2 times -3 minus 3 times 1. Hopefully we get a -9. Let's see. Multiplication first, so 2 times -3 will give me -6. -3 times 1 is -3. That will work. Testing in my second equation. Looks like I'm gonna like this one. -3 plus 1. I think this is one step and it's done. No multiplication to do here because the coefficients of x and y are already 1. So -3 plus 1 is in fact -2. That's going to work out. Again, you can see both in the graph and through the work that we have here that your solution is going to be -3, 1. Alright, so let's take a look at two examples where we're actually going to have to complete the whole problem. Up until this point, I've been giving you just little steps at a time, right? So here's a plane, coordinate plane, no pun intended, and then we have our system. So the system is -2x plus y equals 2, and x plus y is equal to -1. So we want to see if we can solve this system by graphing. I think once we're done solving here, I'm not going to do the check this time. I think you've had a few examples to understand how that works. So we're just going to solve and write down our final answer. So when you're working through these, remember the easiest way to graph your equations is to use slope-intercept form. Y is equal to mx plus b. So if your equations are in standard form, as these are, sometimes it takes a little bit of background work to be able to get them in a slope-intercept form. So I'm just going to take that first equation and I'm going to write it down here. So if I want to rewrite this equation in slope-intercept form, I'm going to have to use my inverse operations to rearrange the terms around so that it looks like y equals mx plus b. Here I'm going to have to move my x term. Since it's negative, I'm going to add 2x to both sides. So that'll cancel here on the left, so I'll just be able to bring down my y. And these are not like terms, I cannot combine them, so I'm going to write them both down on the right hand side. Remember, we're going for slope-intercept form, so I'm going to write the term with the x in it first. So this is 2x, and since that's positive 2, I'm going to write plus 2. Sometimes, if you remember, we have to divide at this point, but because the coefficient of y is just a 1, we're done. It took one step to rewrite that in slope-intercept form. So now that we have that, we can identify the key pieces of information we need to graph. The slope m is 2 over 1. We make it look like a fraction, so we remember both rise and run. And then our y-intercept happens to also be 2. Okay, let's do the same thing for the second equation. So I'm going to write that in this column here. X plus y equals -1. So again, I need to move my x term to the right-hand side, and my goal is slope-intercept form, so I'm going to have to subtract x on both sides this time. That'll allow those x's to cancel, and I have y equals -x minus 1. So my slope, remember if there's nothing in front of the x, there is a 1 there, so this is a slope of -1 over 1, and a y-intercept also of -1. Okay, so now we can take this and we can use that information to create a graph. I think I'm going to use orange and blue here. So if I want to graph here, I'm going to graph the first equation. I need to plot a point on the y-axis at +2. So I go over here, plot that at +2, and then my slope is 2 over 1. So I'm going to rise 2, 1, 2, and run 1. That puts that right here. And then I'm just going to keep following that pattern to create my graph. If I want to go the other way, I'm going to go down 2 and to the left 1. Okay, and I should be able to draw my line. Alrighty, and then I'm going to use blue for the second equation. Another instance where the y-intercept and the slope happen to be the same thing. So plot a point at -1 on my y-axis. That would put a point right here. From there, my slope is -1 over 1, so I'm going to move down 1 and to the right 1. Alrighty, well I can see that if I continue moving to the right that those lines aren't going to intersect there. This is the point where they are going to intersect. So I'm going to keep graphing to the left here. And I'll extend my line all the way across here. Alright, so I have my 2 lines graphed, and I do have them color-coded, but one thing that we need, I don't know if you noticed this in the last graph that we had, the equations were labeled. I'm okay if you don't write out the entire equation. If you number your equations in the system like I have been doing when I'm showing my work, I'm okay with you labeling your line with the number that coincides with the number on your equation. So I'm just going to label 1 and 2. Alright, so final answer. Looks like these 2 lines intersect at the point -1, 0. That's my final answer. If I wanted to check my solution, I could take that value for x, that value for y, and substitute it into both equations just to confirm. Let's take a look at another example. So this time the system is x plus 2y is equal to 0 and -3x plus y is equal to -7. Again, I find it's much easier to graph if our equations are in slope-intercept form, so I'm going to go ahead and one at a time use my inverse operations to change the formatting here. So far they're in standard form. So first equation, x plus 2y equals 0. I have to move that x term to the right-hand side, so I'm going to subtract x on both sides. That leaves me with 2y is equal to -x. I can put the plus 0 there, but adding 0, that's not going to affect anything, so I'm just going to leave that out there. Okay, this time I have something other than a 1 in front of my y, so I do need to divide. And what I do to one side, I must do to the other. So the result of that would be y is equal to -1/2 x. And remember, this is like a plus 0 at the end, so when I go to identify my y-intercept, this is one that's going to pass through the origin. My slope is 1/2. Okay, second equation, same process. So I have -3x plus y equals -7. This time I need to add my 3x to both sides. That will leave me with y is equal to 3x minus 7. Didn't have to divide this time. So my slope, now that this is in slope-intercept form, is 3/1, easy to identify. And my y-intercept here is -7. Now that I'm all organized and I have all the information that I need to produce a graph, I'm going to do the same thing. I'm going to use orange and blue. So for the first equation, this one passes through the origin because my y-intercept is at 0. So I'm going to plot a point right there at the origin. There it is. And then slope is -1/2. So I'm going to go down 1 to the right 2. So down 1 to the right 2. That would place a point right here. And again, we just follow that pattern all the way across the coordinate plane. I tend to plot more points on my first line that I graph than my second, because when you graph your first line, not really sure where the two are going to intersect. So the more points you plot, the easier that will be to see later. Okay, one line down, switching to blue. This time I'm plotting my y-intercept at -7. So here's my y-axis, find -7. Plot a point there, and then my slope is 3/1, so up 3 to the right 1. 1, 2, 3, 1. 1, 2, 3, hey, that's where they intersect. 1, 2, 3, 1. 1, 2, 3, 1. Keep on going. Alright, here's my second line. I'm going to include my labels. So what will be my final answer? Well, the point of intersection of those two lines would be at +2 for the x and -1 for the y. So my final answer should be 2, -1. And if I were unsure if I had done that correctly, I could take that x value of 2, that y value of -1, and substitute it back in. Thanks for watching. If you like this video, please remember to like and subscribe. If you have any questions or suggestions for another video, let me know in the comments below.